let's see where we finished last time. We basically discussed several things. First was accelerated frame. In this case, we said, well, let me remind you what we have done. We just said that we can going to accelerated frame means going to coordinate call it tau. And we also introduced the notation as e to the z. We saw that it's just passing a hyperbolic analog of polar coordinates. And the metric in these polar coordinates is just e to the 2z dz square minus d tau square. And the observer actually moves from the point of view of the original Minkowski space. The observer moves with constant acceleration if in these coordinates, in this frame, it stays at constant z. If it stays at constant z and tau develops from accelerated frame point of view, it's just the observer is at rest because z is not changing. While from the Minkowskian point of view, he is moving along the hyperbola. Okay. And then it is, so far there is nothing much surprising. Then we wrote down the Hamiltonian. The Hamiltonian is for a free field, it's 1/2 canonical momentum plus dz phi square. And this part is not actually affected by passing to the accelerated frame plus this term. And at the first glance, we should, if we describe an observer in this frame, we should be saying that we have the vacuum, which is the ground state of this Hamiltonian, and there are excitations on this vacuum and so on. But that's not what really happening. Namely, so what I said last time is that the vacuum green function for this Hamiltonian, if we take the expectation value tau 1, 5 tau 2, and we average with respect to the ground state, it's not the green function which we obtain by requiring that the whole Minkowski space is in the ground state. So what I'm saying is that we have the coordinates, say it's x0, this is x1, and we have the light cone. And these coordinates cover, these observers cover only this part of this diagram. And to say that this wedge is in the ground state, it's not, we will by saying this, we will obtain a certain green function. However, we know, on the other hand, that we are in Minkowski space, so we have the green function of the Minkowski space. And this green function is quite different, turns out. Namely, if you take the interesting identity is that Minkowski ground state, we can take T product of phi Z1 T1, phi Z2 T2. So in this way, we just actually restrict we restrict the full Minkowski green function to the wedge. The whole Minkowski space induces a certain green function here. And if we do so, we will not obtain this one. As I actually explained, and I will talk a little more about it, what we will get is the thermal green function for this thing. So it will be actually to be precise, divided by the partition function, and here we have.
Can you precisely define what do you mean by this Minkowski?
Okay, yes.
It's not quite clear.
We have Minkowski space, and we are interested in the green function, which depends on x1 and x2, which are these x coordinates. We know that if you have if Minkowski space in the vacuum, if it is in the vacuum state, then it is homogeneous. All points of the vacuum, it's invariant under the whole Poincare group, and then it is a function of x1 minus x2 square. For example, for the masses case, it is the green function is the T product for Minkowski vacuum is this. And if you have massive fields, it will contain this thing. Now the question is, whether we actually we can restrict this green function by replacing x's by those things. I actually did it last time. And so you will obtain a certain green function, which I denoted by this, G Minkowski of Z1 T1, Z2 T2. So I just substitute, doing nothing but substitute this thing into the and then I will certainly obtain a green function of the Klein-Gordon equation in this metric. It will be a green function, but there are infinite number of green functions, generally speaking, and some miracle, which is actually quite obvious, very easy to see, is that the green function which we obtain here by restriction corresponds to the thermal green function. Let's call it, it's called sometime Rindler space. So how to see that this is indeed the case, and what does that mean? In fact, physically, that's the so far it's a formal mathematical statement. The formal mathematical statement is that when you restrict, you have a Hamiltonian in the accelerated frame. It's basically what we are dealing, as I stressed several times already, we are dealing with frame-dependent vacuum, like we had in superfluids. We go to the moving frame, and the ground state is not a ground state anymore. That's what happened in the case of superfluidity, and also in other cases. Here it's to some extent similar. When we go to accelerated frame, we are not in the vacuum anymore. We are in the thermal bath. And I shall explain it better in a second. But it's important to understand the statement. And we start with, as usual, mathematics is easier than physics. So we start with the mathematical statement, which is just the claim, this claim. And I actually calculated last time what happens. I will not repeat this calculation. What happens if you just plug in these coordinates? And the main point is that the green function we obtain. What's the proof of this statement, mathematical proof? The green function we obtain in this way is actually periodic in imaginary time. And as I will explain in a moment, it means thermality. But let's first understand why it is obvious that the green function, it doesn't require any calculations to check that the green function obtained, induced from the Minkowski space. This green function actually is periodic in imaginary time. How do you see this? It's enough to look at the blackboard and to see the formulas. Yeah, it's just because this, when you change tau to tau plus 2 pi I, these things don't change. And that means that the whole thing will be periodic in imaginary time. Now, a physical question, I assume you know the statement. I will that if you have the green function periodic in imaginary time, then it describes a thermal state. But I shall give you some physical understanding of why is that so.
Wouldn't this mean that any object, any green function you compute in these coordinates will have, it has this periodicity, right? So
yeah, well, but if it is if it is true, what you said is correct, provided that the green function has no singularity at the horizon. The point is that this green function, if x1 square is 0, so you are at the boundary of space, is completely analytic. There is nothing happening because x2 we keep x2 non-zero. There is, of course, singularity when at the coinciding point, but that's not what I'm talking about. I'm talking about the singularity of the green function, of the function g, x1, x2. Turns out that almost all green functions except this one, they are singular simply when you set x1 squared to 0. In z coordinates, it means that we go to z to the infinite z. Okay, now if you have, for example, an expression which, if you allow singularity, you immediately lose periodicity. For example, you look at the coordinate arc, the inverse sine of x naught. It will be simply tau. So the statement which I made, it's a good comment which you made, the state is correct provided that green functions are analytic functions of x1 and x2, and they don't have singularity at infinity. Infinity in this case is this light cone boundary. As a result of it, we will get the green function, which is completely periodic. And the only thing I have to explain is why periodicity in imaginary time means thermal. How would you explain this, by the way? What would be your favorite way of? Why we say that? Yes.
The usual match between statistical physics and particle theory.
Yeah, but it does explain much. Of course, you get the good standard way. I shall tell you the standard way, and then intuitive way. The good standard way of understanding this is the following. So we have some thermal average of those things. Let's set to 0. Oh, okay, T2. Then we plug in a of t e to the iht, a e to the minus iht, and then we use cyclic symmetry of the trace to show that a of t1, b of t2 is equal to b of t2. If it was not for this factor, well, the statement would be simply that a of t1, b of t2 is equal to b of t2, a of t1. Here you have to shift by I beta. And when you translate it to the T product, to the chronological product, it means periodicity in imaginary time. That's something. This is the standard part. I shall not go further here. You can find it in various textbooks. It's sometimes called a KMS condition, Kubo-Martin-Schwinger condition. Instead, I will tell you what is the intuitive meaning of this formula. By the way, one interesting thing, before I tell you the intuitive meaning of this formula, as an exercise, try to find the classical limit of this formula of KMS. Try to define it reasonably and to find it should contain the Poisson brackets. I will give you a hint. Anyway, what is the intuitive meaning of this formula? It's the following. Let's suppose that, remember when we discussed conformal field theories, I mentioned the processes when you have E plus, E minus annihilation into many particles. And the total probability will be proportional to, and this is just the Fourier transform of the product of two currents. I'm going quickly and schematically here. Now, here we assume that, let's call this function g of omega. This is the amplitude for absorbing a photon and the system absorbs it and actually creates these particles. Now let's suppose, and here of course, since we are in the vacuum, we can absorb the photon, but we cannot create the photon. And of course we can write down this as actually, after we integrate, we have delta function of omega minus En minus E0. So this, and we said that anomalous dimensions actually define many properties of this process. Now imagine that we have, instead of this setting, we have a system at finite temperature. Then the simple thing to do, which we have to do, is, so if we have finite beta, we have just sum over n and m, e to the minus beta em, mj, and square delta function of omega minus En minus E. Notice that here this function, it's sometimes called absorptive part. It's imaginary part of the T product green function. When we have this, it's non-zero only for omega greater than 0. While here, which corresponds to the fact that we absorb photons only. Here we have both omega greater than 0 and omega less than 0. And if you look at this formula, you immediately find that g of omega is actually equal to, it is related very simply with g of minus omega. And this is just the detailed balance which you see immediately. Do you see how to derive this formula from here? It's actually simply interchange n and m. When you change omega, and you get an extra factor, e to the beta omega from here. This is now what this formula means. It means the very simple thing. One of the application of this formula is just the Einstein relation between absorption and emission, Einstein and Kirchhoff. If you look at the absorption, you have g of omega. And you have to, if there are n photons in this state, you get this. If you have emission, from A equal E, you get the Planck formula. And that's the Einstein beautiful derivation of this Planck formula. Now, and now what it has to do with the imaginary with periodicity in imaginary time. what I claim is that this formula is just means this periodicity. When you go, we don't have time for the details, but if you go to the complete green function, you will obtain the relation that at imaginary frequency it is omega and minus omega will be identified there. I will not go into details. Look what this formula means, what it tells you about the function g of I omega.
Is there a branch cut?
Yeah, it has branch cuts, but it says something more than that, that it is non-zero only when beta omega is 2 pi n. So it contains the Matsubara frequencies only, and you replace the integral over omega by the discrete sum over omega, and that's the standard answer for finite temperature. The reason I'm going through this is that I think it's good to understand its genetic relation to the Einstein formula for real frequency. When you analytically continue to imaginary, you get this. More generally, it's a small digression. With a green function of a system at finite temperature, it looks like as following. Without temperature, it has, so let's consider function t and x, which are differences between 1 and 2. And we have, of course, we have singularities on the light cone at these points. So you have some, generally speaking, branch cuts or poles. It's a complex plane of time. The green function corresponding to finite temperature is different from this in the following way. It must be periodic, and so it has pairs of branch points here and here, here and here, and branch cuts. And there is only one analytic function with these properties, from which you can obtain all kind of matrix element. You can obtain T product. That's like in the vacuum. In the vacuum, we have one analytic function, and T product, retarded product, simple product. They are just different way of taking boundary value of this function. So that's the same thing is true in this case. A good example, by the way, of the thermal green function for you to remember is for the massless field. Massless field g of t and x is sum over n strictly speaking, it should be I beta n square minus x square. So this function, as you see, is explicitly periodic, and it is a green function. When you apply the Klein-Gordon operator, you will get the green function, and this corresponds to finite temperature. And that's basically the end of the digression. We return now to this to this thing, which is actually teaches us a lesson. Maybe one more extra step for this accelerated observer, and then we will go to the case of black holes. which are basically the same. In principle, you can study almost everything in this simple case. In the black hole case, it's just the black hole, and the Caesar case is just the same frame dependence of the vacuum as we have here. Okay, one more comment about this thing. Let's try to describe this. So far we got the kind of a mathematical statement, but let's consider an observer which moves along hyperbolic trajectory. And we can describe this observer. I introduced already before the static field. In order to describe, in field theory, in order to describe particular trajectory, you have to introduce very heavy fields. We saw that in the case of the Wilson loop, we actually need a static particle which is guided along the loop. So roughly speaking, when we have the point of the matter is that we have in quantum theory the green function is the sum over all possible trajectories. So for the normal fields we have the relation that it's the sum over paths connecting x1 and x2 with the weight e to the action. And for the in the classical limit, when you take the mass of the particle to infinity, it reduces to the saddle point. And so we just have one particular trajectory. And if we apply external field, we can actually make this trajectory whatever we like, as we did in the Wilson loop case. So let's look, in order to describe the experience of this observer, we shall imagine that it has some device with two states. And we have two heavy fields. So we have psi alpha. Alpha is 1 and 2. And let's suppose, so we have the Lagrangian of the fields themselves, which is psi 1 dt plus psi 2 plus the important thing is to have two different masses. So in other words, our observer can be in two states, and we want to know whether this formula, which is basically the Boltzmann distribution, whether this formula will be right. In other words, suppose we start with a vacuum for this observer, we start moving in accelerated frame. The question is, what is the probability to fight for the excitation of to the state 2? So suppose M2 is greater than M1. And it is actually very easy to see if we have now the current which interacts with the external field. Suppose we have external field A, and we have the current. This is the bare Lagrangian, this is the interaction. And as we discussed already, I shall not repeat this discussion, we basically end up, we have the A field, and this is the trajectory of the observer. and the probability is given by basically the same formulas. The probability for going along the trajectory will be the following. It will be proportional to A of x of tau 1, B of x of tau 2, A of x of tau 2, d tau 1, d tau 2, to the I omega tau 1 minus tau 2, where omega depends on which omega is 0 if if we look at the diagonal elements, and omega is m2 minus m1 if we go to this thing, and so this is literally the formula we had last time for the for electromagnetic case, but it's precisely the same. The only difference in electromagnetic case in the Wilson loop is that you have x dots here and x dot here. Otherwise, it's the same formula. Now, because of this green function is periodic in imaginary direction, you immediately derive the relation that the probability of the state 2 and so I don't have time to go into detailed calculation, but it is basically the same calculation we did last time. And it's basically the calculation of this diagram. You see, you get where this thing comes from. These are the ends of this A propagator. And this line corresponds to a hyperbolic trajectory. So we get, or to any trajectory, we get this result. In Minkowski space, by the way, if you substitute this thing, if you simply take x of tau v tau, if we go to the observer with constant velocity, not acceleration, we will get, well, I leave it as an exercise. The answer will be the following from this formula. The answer will be that in normal situation this integral is 0. However, if you imagine for one moment that you are moving with a speed larger than light, then you will get the Cherenkov radiation from this formula. So one of the exercises get the Cherenkov radiation from the it's one of the versions of the Wilson loop, actually, when you take classical trajectory and look at it. There are many things which are many technical things which have been understood, and many ideas ideological things which have not been understood here. So it's not that it is completely finished subject. In particular, no one took the Hamiltonian, which I wrote down, this Hamiltonian, and showed that the vacuum is unstable and it will start radiation in such a way that it will end up with, and which will thermalize. No direct dynamical demonstration of thermalization is not present. By the way, how would you explain that the particles here are unstable? The particle states in these Hamiltonians are always unstable, and you can see it from the formula immediately, which means that one elementary excitation always can decay onto some others.
In the Hamiltonian, in the accelerated frame?
No, it's already in accelerated frame. So we can just now, we derived it from accelerated frame, and now we simply forget where it comes from and take it as a...
Because the spectrum is continuous?
Yeah.
Continuous?
Well, yes. Basically, you can, if you have some particle at some position Z, there are other positions where particles are lighter. So it can decay onto these particles. And these particles can decay to even lighter particles. So you have a cascade. And presumably this cascade will lead to thermalization, but that, as I said, is not known.
So you mean if we treat it as a dynamical problem, say, like as a kinetic equation, in
Yes,
a kinetic equation
yes,
approach,
yes.
we might try to
Yes,
find thermalization.
yes, I think so, yes. It's an interesting problem, actually. Okay, now let's look at the black hole case. It's very similar, and I shall explain why. When we have the black hole, we have two observers. One, this one, and the other, the hyperbolic observer, accelerated observer. In the case of black hole, we also have an observer which is outside of the black hole, and the one which falls freely into black holes. That's the second observer. Now, what formulate the analogy? What is? I claim that these two observers in the black hole case, one which is held outside and the other which is falling, analogous to the two observers here. And who is who? Okay, I shall repeat the question. We have, in the case of accelerated frame, we talked about two observers. One observer was staying at rest in Minkowski coordinates. The other observer was staying at rest in accelerated coordinates. By accelerated coordinates, I mean this.
The guy who is falling is the first one.
Yes, why?
Because the guy outside will never see him crossing the horizon.
Okay. In fact, yes, and you can explain it simply by saying that this guy, it experiences external force. So it is this external force which is needed to keep him outside. If you don't hold him, it will go down here and will fall. So it experiences the force. And that's analogous to this guy who is also experiencing the force which is needed to accelerate him. Okay? And indeed, the situation here is that when we have two observers, and suppose two of them hold thermometers. By thermometer, I mean this two-level device. So when we go to this accelerated case, what will be the so if it is so what will the thermometer show of these two? These two guys.
The first guy will have zero temperature.
Yeah, of course. This will have zero temperature, while this will have temperature which is equal to pi. In fact, it's we set acceleration to 1. We took the units. If you have in normal units, the temperature is A divided by 2 pi. And that's what will be the result of this guy, while this is in Minkowski space, quietly at rest, and so on. So analogously here, this guy will not experience anything. It moves, and he will not meet any radiation, while this guy will actually see what is called the Hawking radiation. Now let's try to understand it better and more dynamically. Well, first of all, let's remember the metric of the black hole, and we will rewrite it in some different way. So the metric of the black hole, the standard metric is the Schwarzschild metric, is this one. This is the black hole metric. Actually, it will reduce to the accelerated metric. Accelerated matrix was and I shall also compare it to yet another metric which correspond to the theta space. The metric is it's the space of constant curvature, and the metric is you see that there's a lot of similarities here, and to make them even more impressive, we'll take a different coordinate system. The different coordinate system is the so-called Painleve coordinates. We can write down the Schwarzschild metric, the black hole metric. We can write it down as dr Now let's transform this, and in this form, these two metrics are both of this type, and I will explain where it comes from. This metric is quite remarkable. It really describes the Lagrangian coordinates for the particles near a black hole.
Where does it originally come from?
What?
Where does it originally come from?
Well, it comes from a guy called Painleve.
What was the problem that he was studying?
Well, I think he has a wonderful problem and statement in his paper, because his statement was that Einstein's relativity doesn't make sense because we change coordinate and get something totally different. So it was he was a mathematician, you know. Anyway.
Is it like a diagnosis?
Anyway, let's see the connection. It's very simple. Here we have v square, the term, in the coefficient in front of dt square in this case. Well, the coefficient in front of dt square is minus 1 minus v square of r dt square. So we will, if we simply now identify 1 minus v square of r with 1 minus 2m divided by r, or with minus r square here. That's the first part. But we have there are different terms here, of course. You have the term, this is the first thing. The second thing, you have the cross term here, minus dr dt v, which you don't have here. But on the other hand, you don't have the coefficient in front of dr square is simply 1. All you have to do to recast this thing is to change t to t plus f of r. If you then you get the term dt minus plus f prime of r dr square, and you simply choose f prime in such a way that the coefficient the coefficient in front of dr square will be 1. And after that you will identify these two metrics. So they are completely equivalent, and they have a quite remarkable interpretation and analogy. V of r, as you see from here, how would you interpret V of r in this formula? Look at the equation satisfied by V of r.
Satisfied, you mean?
Yeah, well, we started with the standard expression for the black hole with the mass m, and by changing coordinates, we reduce it to this form, and V of r is given by this form. What?
It's kind of like gravitational potential.
Yes, it actually, the velocity, non-relativistic theory, you have mv squared. V square is simply the velocity of the body falling to Earth from the outside. R is actually 2m divided by r. This is the case of black hole, and V of r is simply r, or if we introduce the Hubble constant, it's hr for the de Sitter space. This describes the expanding space, and the horizon is the point. What is special for the horizon point here? How you define the horizon in these coordinates?
V equals 1.
Yeah, then the velocity of the falling body reaches the speed of light. V equals 1 is the horizon. Now, it is easy to see that the geometry that's easier. Let's, again, you see, I will tell you several different approaches because for the reason that there is no final solution available for the black hole problem. And so it's good to know various. So let's look first at this thing. And let's consider the properties in imaginary time. That's the easiest and the most standard approach to derive the Hawking temperature, is simply to look at the geometry to change T to IT. And to notice that then you have a Euclidean metric, and to notice that this metric has, let's suppose we drop this term, it is the famous geometry of the cigar, where T is the angle here, and there is no problem here of the horizon, because and this apparent singularity is actually out, because R should be considered greater than 2m always. And that's the complete geometry. You see, that's the one crucial point. By the way, you see how to understand that the tip of the cigar is the horizon. How you see it from this formula. Well, time t is periodic. It is this angular variable here. How, by looking at this term, you conclude that actually the tip of the cigar is the horizon.
It's like the origin of polar coordinates?
Yes. When r is equal to 2m, you change t, but nothing changes. And that's precisely what happens here. You see, when you are here, you change t and you go around the cigar. Mm-hmm. But when you are here, you don't do anything. It's all contracted. So, and if you just write down r as 2m plus x, you will reduce plus x plus rho square. You will reduce it near or to the standard thing. It's even more clear in this case to derive. Again, it's all the same thing. To derive the thing for the de Sitter, you start from a sphere. And on a sphere, you have the coordinates, which you can write down d theta square plus sine square theta d omega square plus cosine square theta d tau square. So here you have it's generalized polar coordinates for multidimensional sphere. That's kind of what theta is, just the azimuthal angle. Tau is the analog of the polar angle, and so on. So that's trivial. And now to get this, and as you see, the metric is completely regular. All you have to do is to set r equal to sine theta, after which this term will be dr square 1 minus r square plus r square d omega square plus 1 minus r square d tau square. So as you see, we got the same metric in imaginary time. But this time it's not a cigar, it is a sphere. And for the metric to be meaningful, tau and tau plus 2 pi must be identified. So we have periodic, all which is to say that all green functions which are regular on a sphere, if you have a green function on a sphere, you express it in terms of those coordinates, and if green function is non-singular, it will be periodic in tau, and that gives you what is called the Hawking temperature. But let's go a little deeper into this. So it's mostly kinematics, and the kinematics is the same in the case of in the accelerated case, the black hole case, and the de Sitter case. And another common feature here is that the horizon, there is no horizon problem in the Euclidean case because horizon is a point. But it's quite questionable whether we can whether it's enough to use Euclidean theory to go to the Minkowskian space, because in Minkowski space the horizon is not a point, it's a surface, and the question arises what is inside this surface, and Euclidean theory gives you only the outside of the horizon region. So one would like to have more physical understanding of this radiation, and that's what I will try to do now.
Can you go to the Euclidean section from the region behind the horizon? If you start from
yeah, in principle you can, but you see, it could be you can in this case you have to this term becomes negative, this term becomes positive, so you have to think there are different possible analytic continuations which you have to think about, but it's not by simply changing time to I time. You will do you no good, because you see, if you will get a plus here if you change t to it, but for r greater than 2m it's a totally disconnected from the cigar space, disconnected from the cigar. You may think indeed whether you can what can you say about this space inside the horizon, but you cannot use the argument that this is the same thermal state, because there is no periodicity, and you need some extra information. Like, for example, you can say, let's go to the let's take the Kraskell solution, which is the maximally extended black hole, and see what happens inside it shows the inside horizon, but it's not present. It all compressed to one point when you go to the Euclidean sections. The horizon compresses to one point. So.
But it's not like the both sides they just wrap the Euclidean section twice or something.
No, that's not the case. All right. So let's try to compare it with certain electromagnetic problems. It is well known that there is, and that's basically, there are some analogies between electromagnetism and this, and hydrodynamics and this. By the way, the first interesting point, I will not have time probably to discuss hydrodynamics. I will just mention to you one, I'll give you one interesting exercise. Take this metric, the pendulum metric, assume that V depends on R and T in general, and calculate the curvature. And I will tell you what is striking about this result. So the curvature will be some function of derivatives of V and so on. So you have standard rules according to which you calculate the curvature. What is extremely interesting and intriguing is that if you set this curvature to a constant by introducing some cosmological constant, then V will satisfy a certain differential equation, of course. This differential equation will be the Navier-Stokes equation. So that's the full meaning of this, I think, is unknown, but it's certainly interesting. So try to you can, as a first step, you can try to drop this term and calculate it in 2 dimensions.
What will be friction in this case?
Well, actually, the friction, I think, will be related to the cosmological constant. There will be also cases without friction. Actually, I don't quite remember what. Maybe I cannot answer this question. I did it long ago. The key point, the only thing, so do this exercise and check it. The only thing I do remember is that quite surprisingly you get this typical left-hand side of the Euler equation. And then I think you get also the friction term, but which depends on which equation you have. It's probably, I never thought it to this example to the end. Probably it could be expected from symmetry, because there is something like Galilean symmetry here. So maybe it's not so surprising after all, but at least it gives you a possibility to build some hydrodynamic analogies of gravity. Okay, but let me, I digressed as usual. We now look at the electromagnetic analogy. Electromagnetic analogy is that when you have, suppose we have electric field, scalar electric field, and then you have particles satisfying Dirac equation or Klein-Gordon equation. The Klein-Gordon equation in this field will be simply Dirac equation is slightly different, but then you have the following situation. Let's look at things semi-classically. Without field, we have the spectrum of this operator so we have omega and p, and we have 2 bands. The vacuum, which according to Dirac is filled with particles, and this is the valence band, this is the conductance band in semiconductor analogy. Now let's apply the field. if we apply the field, we have the semi-classical expression for omega, which is given by A0 omega plus and minus. And we see that we can actually create a pair. We can create a pair by taking electron here, forming a hole, and placing it here. And without external field, the energy needed to create a pair is obviously 2m. So at A0 equal to 0, delta E, the energy needed to create a pair, is 2m. And indeed, this is the case. You can use the photons or some other particles to generate E plus and minus pair. But now, when we have A naught non-zero, delta E will be equal to the minimal value of omega plus of P and X minus maximal this is because it's profitable to create a particle at such a position where its energy will be as small as possible. So this is a very general formula which will hold not only for this case but also for that gives you the following. If you take if you look at this formula, then minimal omega plus is A0. Let's take A0 of x growing. So A0 for definiteness is something like that. It will be A0 at minus infinity. We want the minimal value of this guy plus m. And this is A0 at max of omega minus will be A0 at plus infinity minus m. So we see that delta E is actually negative. If the potential difference is greater than 2m. Same thing, by the way, happens in the semiconductors, where you have precisely this type of picture. And in semiconductors, it's called Zener breakdown. And actually, there are diodes which work on the basis of these Zener diodes, which work because of this breakdown. So it's a very real thing. And we see that if the field is strong enough to create pairs, we have instability. There will be this pair creation. It will also be an instability of the same origin. If you have a nuclei with a charge Z, then the picture is the following. We have the nuclei, we have the electron rotating around the nuclei, and of course, if you try to create the energy of this thing is will be for small coupling, for small charge, is the energy is greater than the energy of bare nuclei. But now consider a bare nuclei. It will be stable if, and consider the following possible process in which you create a pair E minus and E plus, and E plus goes to infinity. Then if the binding energy, then what's the energy balance here? Delta E, we lose 2m, but we win the binding energy, which depends on Z. When it is greater, when it is less than 1, you will start radiating. The nuclei becomes lighter than the atom. Excuse me, it's always lighter. The atom becomes lighter than the nuclei. So it's the other way around. So you will have, if you have many levels, many electrons, and all these levels have this binding energy restriction, then what you will see is the flux of particles from this nuclei until it is neutralized. And that's an analog of the black hole. Well, we're getting late a little bit. So this is the electromagnetic. The last point I shall make is what is the analog, what is the gravitational analog of this thing. And we can read it from this metric, from the black hole metric. So you see the origin of, it's the analog of Hawking radiation. When you have very heavy nuclei, there is just flux of particles, flux of positrons going to infinity. And it ends when the nuclei is neutralized. Now the last point is that if we look at this metric, it's very easy, and again it's considered as an exercise, to write down the Klein-Gordon equation in this metric and to derive the analog of this. So we have here, we had omega plus minus A0 minus p square plus m square. In the case of this Painleve metric, this formula remains true, but omega plus minus is p v of r plus or minus square root of p square plus m square. And by the same type of analysis, you find that in this case you have instability if there are points where v of r exceeds the speed of light. So when v of r is greater than 1 somewhere, then there is an instability of precisely this type. Namely, it's just energetically favorable to create particles. Okay, let's stop here. We'll try to conclude it somehow tomorrow.
But if v of r is always less than or equal than 1, then there's like some, just like that Dirac point in graphene, there's a
Yes, yeah, it's more, yeah, well, in this case, it's indeed, if v of r is less than 1, it's an interesting case. And actually what I'm doing now is trying to understand what happens, what kind of singularity we have when v of r tends to 1, but remains less than 1. It's much more well defined in this case. So the analogy here, indeed, when we have two bands, when it's possible to have this intersection where this valence band turns out to be here, and that's condensed matter. People call these semi-metals. Because you get, you see, this was occupied, but it's clearly unstable state, because you will have recombination in which the holes here will be filled with particles here. But that's not all. After that, there is the situation when this semi-metal turns into what is called excitonic insulator. Namely, these excitons are the bound state of particles and holes, which is in particle physics is positronium, bound states of electrons and positrons. And there have been for a long time the statements that because of the interaction, these particle holes excitons, bound states, are unstable. They are like Cooper pairs. So there is a Bose condensation of this. There is definitely some instability here, which even after this naive recombination occurred, you still have unstable system. To what extent? So it's very subtle, but it's the fact that's experimentally. It was predicted theoretically, and it was observed experimentally.
It's for low temperatures.
Huh?
It's for low temperatures.
Yeah.
So you mean that
It's actually the what? Sorry.
So some of the semi-metals turn out to be excitonic,
Yes,
provided
insulators.
provided
It
that
depends on interaction. There's a nice original paper by Keldysh and Kapaev long ago, and recently people actually experimentally found that it happens. But you see how little we know about there. Even in much simpler system, there are all these subtle effects, and nothing. We are far from this level in the case of black holes and the City space. There are many subtle effects which still wait to be discovered there. And the analogy, this analogy, I think helps. Analogy with condensed matter, and this case, the case of the de Sitter, is of course extremely fundamentally important for cosmology. Mm-hmm.